Today's topic is Principal Component Analysis, or PCA for short. If you've ever worked with a big dataset, dozens or even hundreds of variables, you might have wondered, do I really need all of these columns to understand what's going on? That's where PCA comes in. It's a powerful tool that helps us simplify data without losing the most important patterns. Let's break it down from the beginning. Imagine you've got a spreadsheet with 100 rows of data on people, height, weight, age, income, shoe size, cholesterol level, and so on. Some of these variables are related. Taller people might have bigger feet. Higher income might relate to age. PCA asks, can we reduce this messy set of variables into just a few super variables that still capture the main trends in the data? These super variables are called principal components. Each one is a special combination of your original variables, like a weighted average, but carefully chosen to capture as much variation as possible. The first principal component captures the most variation in the data. The second captures the next most, but it must be uncorrelated with the first. And so on. Let's imagine you've got a scatterplot. Weight on the x-axis, height on the y-axis. The points form a cloud sloping up to the right. PCA says, what's the direction in this cloud where the data spreads out the most? That direction becomes your first principal component. It's like rotating the coordinate system. Instead of thinking in terms of weight and height, you now think in terms of PC1 and PC2, new axes that better reflect how the data actually varies. Now, let's go deeper into the math that makes PCA work. We'll take it step by step and keep things intuitive. Step 1. We center the data. That means subtracting the average from each variable so that the data cloud is centered around the origin. Step 2. We calculate something called the covariance matrix. It shows how much each variable varies and how much they move together. For a two-variable case, the covariance matrix might look like this. The diagonal values represent the variances of each variable. The off-diagonal values represent how strongly the variables change together. That's called covariance. Now, here's the core idea. PCA wants to find a direction, call it W, such that when you project the data onto that direction, the spread is as wide as possible. To project a data point, X, onto direction, W, we compute. This gives a scalar, the shadow of the point in that direction. Now, across all the data points, we want to measure the variance of these scalar projections. It turns out the formula for that variance is, here, sigma is the covariance matrix, and W is a unit vector. This formula gives the variance of the data when projected onto direction, W. So now we have a goal. Find the direction, W, that maximizes this variance. Mathematically, that means we want to maximize. Subject to the constraint that this just means W is a unit vector, it has length 1. This is a classic optimization problem, and we can solve it using Lagrange multipliers. When we do, something beautiful happens. The condition for the maximum becomes this. This is the asterisk eigenvalue equation. It tells us that the best direction, W, the one that captures the most variance, is an eigenvector of the covariance matrix. And the amount of variance it captures is the corresponding eigenvalue. Let's say we compute the following. Eigenvalue 1 equals 5.4. Eigenvector 1 is 0.8, 0.6. Eigenvalue 2 equals 0.6. Eigenvector 2 is minus 0.6, 0.8. That means the first principal component points in the direction 0.8, 0.6, and captures most of the variation. The second component captures much less. So we can simplify the data by projecting it onto just the first direction. This is how PCA works. It finds the directions in space, the eigenvectors, where the data stretches out the most. And it tells us how much spread there is along those directions, using the eigenvalues. It all comes from a simple idea. Project the data onto a direction, measure the variance, and find the direction that makes that variance largest. That's PCA in a nutshell. Once we have our principal components, we can project any data point onto them. Usually, just the top 2 or 3 components capture most of the variance, and we can visualize or model the data using just those. Think of PCA like taking the most informative photograph of a 3D object. If you pick the right angle, you can capture most of the structure in a single shot. That's what PCA does. It gives you the best view of your data. The interactive tool we introduced in this video is linked in the description, so make sure to check it out and have fun exploring it yourself. If you enjoyed the video, give it a thumbs up, and if you want more hands-on ways to learn stats, subscribe to the channel and hit the bell so you never miss a new drop. Thanks for watching, and remember, don't just think. Feel the stats.